Welcome to HSEEG.
Construction lifting operations manage extreme physical forces. Every day, operators suspend millions of pounds of steel and kinetic energy over populated urban centers. Operating these machines requires strict adherence to physical limits. A safe worksite demands precise calculations of load moments and gravitational forces to keep massive structures upright under immense stress. In the United States, those physical limits are codified into federal law. OSHA 29 CFR 1926 Subpart CC serves as the definitive engineering envelope governing these operations. The code divides regulations by equipment class. A crawler crane on dirt and a fixed tower over a skyscraper face entirely different gravitational challenges, and the law applies specific controls to address the unique vulnerabilities of their respective architectures. We are going to deconstruct the four primary lifting systems, mobile, tower, derrick, and marine cranes, to locate their specific points of failure. The structural design of the lifter dictates the precise safety controls required by law to prevent a catastrophic collapse. Compliance with Subpart CC is an absolute structural necessity. It is the applied physics that keeps the site intact. We begin with the mobile crane taxonomy. This category encompasses crawler mounts, wheel-mounted truck cranes, rough terrain, and all-terrain models. Their primary mechanical advantage is geographical flexibility. They can traverse public roads or navigate raw dirt to reach the exact point of need. Because they lack a permanent foundation, their structural stability relies completely on the bearing capacity of the earth beneath their outriggers. Under OSHA Standard 1402, the site's controlling entity bears legal responsibility for this surface. They must mathematically verify the soil is firm, drained, and graded to support the crane's exact load specifications. For mobile machinery, lifting operations actually begin in the soil mechanics, long before the boom is raised. Moving vertically, we encounter the tower crane. These fall into three main categories: hammerhead, luffing boom, and self-erecting configurations. Unlike mobile cranes, towers are bolted to an engineered foundation. Their primary vulnerability comes from extreme height, which amplifies any minor angular shift at the base into a massive displacement at the boom tip. OSHA Standard 1435 regulates these systems, enforcing rigorous checks on their vertical alignment to ensure gravitational forces remain centered. The code mandates an exact mathematical tolerance for plumbness, a 1 to 500 ratio. Section 1435 also mandates active safety technology, including load moment limiters, trolley stops, and wind speed indicators to monitor external pressure. For fixed towers, physics demands uncompromising structural geometry. Micro deviations in that 1 to 500 ratio represent an ultimate point of catastrophic failure. The articulating, or knuckle boom crane, utilizes a specialized folding mechanism, making it highly effective for high-precision material logistics. These machines exist on a regulatory border. If an articulating crane simply offloads packaged building materials directly onto the ground, OSHA does not classify the activity as construction work. The threshold is crossed the moment that crane swings its load over the active structure. Delivering sheet goods directly onto a partially built frame invokes the rules of Subpart CC. Even then, there is a strict condition for exemption. The machine must be equipped with a properly functioning automatic overload prevention device. The boundary of OSHA coverage here is dictated entirely by the precise location and nature of the material transfer. When worksite constraints make mobility impossible, contractors deploy derricks, heavy-duty stationary lifting solutions. Variations include the gin pole, the stiff leg model, the guy derrick, and the Chicago boom. Their core mechanical difference from traditional cranes is how they manage mass. They balance loads entirely through tension distributed across fixed structural foundations. This schematic of a stiff leg derrick shows how the load's kinetic force transfers directly into the anchorages. Before service, a competent person must execute and document functional mechanism and physical load tests against those anchors. Because these lifters rely on external tension, their ability to survive a lift depends entirely on the verified math of their anchor points. Moving away from terrestrial dirt and concrete, lifting mechanics shift dramatically in specialized industrial and marine zones. Under OSHA Standard 1438, temporary overhead gantry systems and industrial carry deck cranes face their own rigorous inspection protocols when integrated into construction workflows. The operational complexity peaks on the water, where floating cranes and standard cranes mounted on barges perform heavy lifts. Marine lifting introduces profound hydrodynamic forces. The engineering baseline shifts from a static ground envelope to a constantly moving fluid surface. OSHA Standard 1437 mandates continuous environmental monitoring to account for wave action and shifts in buoyancy. Operators must digitally monitor two critical metrics during every lift: list, the side-to-side tilt, and trim, the front-to-back tilt. Marine operations replace the predictability of solid ground with fluid mechanics, requiring the highest level of continuous, dynamic mathematical control anywhere on a worksite. Despite all the structural and mechanical failure points discussed, the leading cause of crane-related fatalities on construction sites is entirely invisible. Electrical contact with high-voltage power lines kills more workers than structural collapse, and direct physical touch is not required for an electric arc to jump from a transmission line to a steel boom. OSHA's power line protocol requires operators to establish a mandatory work zone. This isolates the crane to determine if any part of the machine could breach the minimum clearance threshold during a lift. If the line's voltage is unknown and assumed to be under 350 kilovolts, the code demands a strict, impenetrable 20-foot barrier between the equipment and the line. If the exact voltage is verified by the utility owner, operators can utilize alternative clearance distances. This table, known in the code as Table A, acts as the definitive regulatory matrix, specifying the precise minimum clearance distances required as the nominal voltage increases. Across every class of machinery, the universal operational mandates remain the same. Operators must never exceed the manufacturer's rated capacity, and every machine requires rigorous shift and annual inspections executed by formally designated competent and qualified persons. A machine's rated capability means nothing without environmental discipline. Surviving the lift requires strict adherence to the engineering envelope defined by OSHA 29 CFR 1926 Subpart CC.
Welcome to the site. We're excited about the progress. Don't forget to like this video and click that subscribe button to follow our journey.